Hi guys, welcome back to Data Every Day. Today we're looking at a data set of flights, US flights from 2015, and we're going to try to predict whether a given flight will be cancelled or not. So if we look at all the columns here, towards the end we have this cancelled column, and we're going to try to predict cancellations based on the rest of the data. So let's hop into the notebook. We're just going to use a simple logistic regression model to make our predictions. So I'm importing NumPy and Pandas to work with the data, PyPlot and Seaborn for visualization, train test split function, and standard scalar from sklearn for pre-processing. Then we'll use the logistic regression model from sklearn, and to analyze the results we'll use a confusion matrix and classification report, also from sklearn. So we'll import all of that, and then let's load in the data using pandas.read CSV. So we're going to be using the flights.csv file. So I'm going to paste that in, and we'll take a look. Actually, this file has like 6 million rows, I think. So I'm actually going to cancel that. We'll only use a subset of the data, just so that our notebook doesn't take forever to load. 50,000 examples sounds good. Alright, and I guess what we can do is start by getting a little info on the dataset. So you can see we have at least some null values in here, and some of these a very substantial number of null values. And we also have a few object columns that we're going to have to encode. So let's start pre-processing. Actually, yeah, pre-processing. So I actually want to make some helper functions. And the helper functions are going to help us pre-process in one go. So I'm going to have a function called pre-process inputs that's going to take in a data frame. It's going to start by creating a copy of the data frame, and at the end it will return the data frame. And then over here we can actually call the function pre-process inputs, and we'll pass in data, which is our df, our data frame. And we can store it in x. So x will be the pre-processed version of our data, and data is the unprocessed version. So up here we can look at data, down here we can look at x. Currently they're identical, but now anything we add to this function, we can then see the difference. So what's the first thing we should do? Well, because we see these columns that have like such a high number of missing values, let's take a closer look at like what percentage of each column is missing. So right here we can get that with data.isNA. This will return a true-false data frame based on whether there's a missing value in a given location. So at the end we have some missing values, and we have all trues there to match up with them. So if we sum over the x-axis, the row axis, if we sum over the rows, we'll get the count of trues in each column, or the number of missing values in each column. So this is nice to be able to understand like how much there is, but it's better to probably use the mean. The mean will add up all the trues and then divide by the total number to give us the percentage of missing values. And so now we can see it in percent form, and this is a lot more informative. You can see this has 97%, and it also, if we were to use this, it would give, it's just an extra target column in a sense, because if there is a value here, I'm guessing that's because it was cancelled. It's called cancellation reason. So a bunch of these we're going to want to drop, namely the ones with a really high number of missing values. So you can pick this threshold how you like, but something around 25% is pretty good. If a given column has over 25% missing values, we can drop it because it's just too much to fill in. So let's actually find that. So if we take this series here, and we ask, is it greater than or equal to 0.25? This will give us all the columns that have more than 25% missing values. And we can actually use this true-false series as an indexer in the data frame. So data.loc, I'm targeting all rows and just these columns. That will return back just the part of the data frame, all the columns that have over 25% missing values in them. And so if I type .columns from that, we'll just get the names of the columns. And so these are the ones I want to drop. I want to drop these columns. So let's take that and we'll plug it into our pre-processing function. And I'm going to call that missing columns. And this is, instead of data, is now df. And now we can say df equals df.drop missing columns from axis 1, which is the column axis. And then we'll return it, so let's see how that goes. Here's our data with all those missing columns at the end. We're now going to run this function and then take a look at x, and you'll see that all those missing columns are gone. We now have 25 columns remaining, and if we just check out the missing values in the x, you'll see that there are no more columns that have over 25% missing values. So, what to do next? Let's drop some of the columns that we don't really need. I guess it's not really useful to see data anymore. Let's just keep x at the top here. And I'll keep this even higher. Okay, so there are some columns here that are not necessary to what we're trying to do, and there's also some nuisance columns. So note that I can't see all the columns right away because there's over 20. So I can go into the console and type pandas.set option max columns none, and that will allow me, when I reload this, to see all the columns at once. And so when we're looking at columns and trying to figure out what's useful or not, it's a really good idea to get the number of unique values in each column. Either get a list of all the unique values to figure out how to encode, or getting just the count of how many unique values are in each one can really help. So let's create a dictionary that's going to map a column name to the length of unique values in that column. So I'm taking x subcolumn.unique to get all the unique values. I'm taking the length of that, and that's for every column in x.columns. So we'll take a look. Alright, and the first thing I notice is that we have some columns here with one value, and when you have a column with one value, it's actually not useful. Now I'm not sure if maybe if we used all of the examples instead of just using 50,000 of them, then maybe we would have some other values in there, but since we are just doing 50,000 for this notebook, I'm going to drop both these columns. Additionally, we can look through. Okay, here's an interesting one. Tail number. So tail number is a categorical column. These are all sort of independent in their own category, and we have 4,000 of them. And so 4,000 columns is 4,000 unique values is sort of pushing it in terms of the one-hot encoding scheme. Now, if you had access to a large amount of time and computational resources, it's probably fine to leave such a high number of features on. But since we're doing just a quick notebook, I'm going to drop this column, because if I wanted to encode this in a one-hot fashion, so if I use pandas.getDummies on this column, which is x sub tail number, you'll see it actually has to now create 4,086 new columns, one for each unique value. And to put that on our dataset and then train a model on it, it's just going to take a really long time. And if you are not trying to squeeze every bit of effectiveness out of the data, it's probably best to just drop this. I would also like to note that flight number is a very similar case. The only difference here is that they're numerical. However, they are categorical, as these do not imply one is greater than the other. So we're actually going to drop both flight number, which has 5,700 unique values, and tail number, which has 4,000. So in here, so let's say we removed the columns with more than 25% missing values. Now under here, we're going to drop unneeded columns. So df equals df.drop and we can just include all the columns we're going to drop here. I said we're going to drop year and month because they only have one column, one value, so they're not useful to us. Year, month, and then we had flight number and tail number. And all the others here look pretty good. I think these are all numerical features. The only exception being these ones, origin airport and destination airport. However, they have a reasonable number of unique values, so we will apply one-hot encoding to them. It's also sort of optional whether you want to one-hot encode the day of the week or the day of the month, because you can consider them all as ordinal features or as nominal features, depending on how you look at it. Because it does go in a cycle, or day of the week loops. So there's some meaning behind using it as an ordinal feature. You can say low values mean the beginning of the week, high values also mean the beginning of the week, and then values in the middle mean end of the week, right? I mean, it does loop, so it's weird. But you can also encode it as a nominal feature, so that each day gets its own column. I think we'll leave it as ordinal for now. Same with day. But I want to one-hot encode these guys. Origin airport, destination airport, and airline, which has 14 values, so it's definitely a candidate for one-hot encoding. Alright. So let's drop these from axis 1 and take a look at what happens. Alright, sure enough, we no longer have the month and week columns. Is that what we dropped? Yeah, no, year and month columns. And we also no longer have the flight number and tail number columns. So now let's do the one-hot encoding. So I'm going to make a function called one-hot encode. That's going to take in a data frame and a column dict. So this is going to be a dictionary that maps a column name to a prefix to use for the dummy columns. So let me just grab this, and I'll use it as an example. So we're going to one-hot encode airline, right? So I'll put that in there. And you can see now that each airline gets its own column, and we get a 1 in the case that the original example had that value. So here we had AS, AA, US, and over here we have 1s in AS, AA, and US respectively. And notice that we can also include a prefix. We can call it air or whatever we like, and that will just put air at the beginning before the airline name. So what I'm doing here by passing this column dictionary is it's going to map a column name that we'd like to encode, for example airline, and it's going to map that to a prefix that we're going to use in the columns, in the encoding. So let's do this. Let's start by creating a copy of our data frame, just so that we're working with a fresh copy. And then for every column and prefix, in column dict dot items. So dot items returns a dictionary's key value pairs as tuples, so that we can index them 2 at a time like this. Then we'll create some dummies. So that's what these are. It's going to be these columns here using pandas dot get dummies, and we're going to use df subcolumn as what we're getting the dummies for, and we'll include the prefix to be the prefix that we passed in the column dictionary. Then we will actually concatenate together the original data frame and the new dummies columns side by side, so axis 1, and then we're going to drop df.drop the original column from which we created the dummies. And that will be it. Then we'll return the data frame, and then in here we can say one-hot encode nominal feature columns. So to do this, we're just going to use our function df equals one-hot encode, passing in df and passing in the column dict, which is going to map the name of a column we'd like to encode to its prefix. So airline, we're definitely going to encode, and we can just give that a prefix of AL for airline. Origin airport, we can give that OA. Destination airport, DA. And I think that's it. I don't think there's any more categorical features here. Yeah, they're all numerical. So let's run that now and see what we get. Alright, we have quite a few more columns now, and you'll notice that all the categorical columns are absent from the data, but if we scroll over here, we have all these one-hot columns that have come from the encoding. So this is still a reasonable number of columns to use. If we had chosen to one-hot encode these guys as well, we would have gotten something like 10,000 plus columns, so I'm trying to keep it low. Alright, and this is what we're left with, and this all looks reasonable. You'll see all the one-hot columns will have 2 values. The cancelled, this is what we're trying to predict. So let's actually before we split the dataset, we should probably deal with these remaining missing values, because there are a few in there. And so let's see. Okay, I'd like to know which columns still have missing values. So let's look at this. Let's do this. We'll get the sum instead. This will sum up the number of missing values in each column, and we'll say if it's greater than 0, we'll get a true if it's greater than 0, and then we'll call x.loc on all rows and just the columns that have more than one missing value, one or more missing values. So these are all the columns with missing values in them. And you can see that these are actually all numeric columns, which makes our life easier, because that means all we have to do is fill in the missing values with some statistic from each column. So we'll just use the mean. You can also use mode or any other that you like. There's some more advanced methods of imputing the missing values, but we'll just use the mean. So fill remaining missing values with column means. Alright, so what I'll do is I'll grab these columns. So we can call .columns to get just the column names. And then let's go put that here and call that remaining NA columns. And I just want to change this to df instead of x. Alright. And then for every column in remaining NA columns, let's take the column and fill missing values using the fill NA function from Pandas. This function allows you to put in a value and it will fill all the missing values automatically with whatever value you put in. So we're going to pass in df subcolumn dot mean. So we're filling each column in the columns with missing values with the mean of that column. So if I run this and take a look, it doesn't look any different, but now if we go in and we check the missing values, x dot is an a. I remember it gives us this true false thing. So if we sum over the rows, we'll get the number of missing values in each column. And if we sum again over the columns, we'll get the total number of missing values in the data set, which comes out to be 0. So we have no more missing values in our data. So that means we also our data is also fully numeric, so we can just scale the data and train our model. So let's first let's split it. Yeah, so let's split df into x and y. So a y will be what we're trying to predict. In this case, it's the cancellation column, the cancelled column. So y will be df sub cancelled, and we'll make a copy of it as well. And then x will be everything except what we're trying to predict, which is what we're going to use to predict y. So df.drop cancelled. And we're dropping from axis 1, which is the column axis, and we'll make a copy. Alright, Now, instead of returning df, let's return x and y. And let's get them over here. Now we have x, which no longer has the cancelled column in it, but we can get that from y, which is just the cancelled column. Alright, and then we'll do a train test split, which will split it horizontally. So we'll use the train test split function from sklearn for this. We're going to pass in x and y and specify a train size, how much of the data we want to go to the train set. We can use 70%, and we'll include a random state as well, because this function actually shuffles the data in addition to splitting it. So by including a random state, we can ensure that the shuffle and the split is always done in the same fashion. So I'll just use 1, 2, 3, it doesn't really matter. And then that will return 4 new values, which will be xtrain, xtest, ytrain, and ytest. So here's our vertical split, and here's our horizontal split. Alright, now let's scale the data. Scale x with a standard scaler. So let's actually return, instead of x and y, we'll return xtrain, xtest, ytrain, and ytest. And we'll get them over here. Xtrain, xtest, ytrain, and ytest. And we'll take a look at xtrain. So we now have 70% of the data only, so 35,000 rows. But it's still all the columns except the cancelled column. And this is what we're going to use to fit our scaler. So a scaler will it'll apply a transformation to each column. A standard scaler, which is what we're going to use today, will give each column a mean of 0 and a variance of 1. And the benefit of that is that currently we have a whole different range of values in each column. In the one-hot columns, we have only range between 0 and 1. And then over here, we have it up to like 2,000. So by using the scaler, each column will have a similar range of values, and that actually helps the performance of a model substantially, most models. So let's scale it. We'll create a new scalar object from sklearn, and we can fit that scalar to the train set. So I'm not fitting it to the test set, just the train set, because in practice, if you were given data to train on, and then the test data is coming in separately, you wouldn't have the ability to retrain, refit the scalar. Essentially, since we're fitting the model, the estimator, on the train set, we should also just fit the scalar on the train set. So once we have the scalar fit, we can transform both the train and the test sets using the fit that we have. So we can do that with scalar.transform, and we're transforming xtrain in this case, and down here we're transforming xtest. Now I'd like to note that this scalar.transform function returns a NumPy array, so I'd like to turn it back into a data frame afterwards. And I'll set the column names equal to be x.columns. Alright, now let's get that. And we'll take a look at xtrain now. You can see it's the same data set, but all of the columns have been scaled so that they have, you can actually take a look, xtrain.mean. All the values are very close to 0. And if we check the variance, you can see they're all very close to 1. Alright, so I guess we can start, we can train our model now. Alright, let's create this training. And basically, we're gonna let's actually well, it's very easy to train it. We'll just create a new model, which will be a logistic regression model. And all we have to do is call model.fit, and we're fitting it on the train set, so xtrain, ytrain. And that's pretty much it for training. Like I said, we're only using one model today, just trying to keep it simple. And then we will show the results. So I could just return the accuracy, but we get a lot more information by using a confusion matrix and a classification report. So classification report basically just gives us more information about the confusion matrix. So what I'd like to do is over here in our helper functions, I'm going to create another one called evaluate model. And it's going to take in model and a test set, x test, y test. And we can start by getting the accuracy. So model acc equals model dot score, and we score on the test set here to return the accuracy value. And then we can print it out, test accuracy. We can display it to 2 decimal places with the percent sign afterwards, and format that to be model acc times 100, so we can see it in a percentage form. Now if we just run this now, parameter names are the same as our actual arguments. You can see it just returns the accuracy. But now I'd like to also return the confusion matrix and classification report. So to compute the confusion matrix, we're going to need a set of predicted values and a set of actual values. So our actual values are just going to be a y-test. So we already have those. They're like the answers to our predictions. And I'll call it y-true, which will just be a NumPy array version of y-test. And then our y-predictions, this is going to be from the model. So we'll call model.predict on x-test. And sklearn by default returns a NumPy array, so they'll both be the same format. And then we can go create a confusion matrix using the confusion matrix function from sklearn.metrics. And I'm going to pass in the true values and the predicted values to compare. And we'll also create a classification report, which I'll call CLR, also from sklearn.metrics. And we'll pass in the true values and the predicted values. Alright, so the confusion matrix, if we just take a look at it, print CM. Classification report. You can see it's very boring looking. It gives us the information we need, but it's not nice to look at. So what I'm going to do is make, I'm going to plot it with a seaborn heat map. So let's go ahead and create a new matplotlib.pyplot figure with a figure size of 8 by 8. Works well for confusion matrices. And then use seaborn.heatmap, and we're going to pass in the confusion matrix, turning on annotations, setting the minimum value that it displays to 0 for the color bar, and then we're also going to format it like so, just because by default I believe it returns scientific notation values, and I just want integers, so this will accomplish that. Then I'm going to give it a color map of blues, and I'm going to turn off the color bar. Alright, so let's show that now. That should be a lot nicer than just seeing this. Okay, we can see it. That is nicer, but it's not labeled very well, so let's go and add some labels. On the X, we're going to have the predicted values. On the Y, we're going to have the actual values. So now you can see, but I actually want to change these 0 and 1 to be more descriptive. I wanted to say the actual class names, which in this case, 0 signifies that the flight was not cancelled, and 1 signifies that the flight was cancelled. So in here, I'm going to adjust the X ticks, which are these tick marks here. And first I have to pass in the position of the tick marks. So we want 2 tick marks, so I'm going to create a NumPy A range with 2 values. That will give us 0 and 1. But 0 and 1 are actually, they mark the locations for the corner and the middle. So I'm going to add 0.5 to the A range so that we get 0.5 and 1.5, and that will mark the middle spots here. Then I'm going to pass in the actual labels to use, which will be not cancelled and cancelled, respectively. And I'm going to do exactly the same thing for the Y ticks. Alright, and then we'll just give it a title and we'll be done. Confusion matrix. Alright, here it is. So I won't analyze it just yet because I also want to print out the classification report. So classification report / to give it some nice hyphens, and then I'm going to print the CLR right after that. Alright, there's one too many hyphens. Not essential, but there we go. Alright, and this is a nice function that will give us 3 useful ways to look at how the model is performing. So now that we have our function, let's call that down here in the results. Evaluate model, passing in model, x-test, and y-test. And now let's look at it. So it's not too bad. There is quite a class imbalance here. If we look at the ytrain.value counts, you can see we have a lot more not cancelled examples than we do cancelled, which makes sense, but that can negatively affect the performance of the model. Now, I did try to use various methods to try to improve the performance by oversampling the minority class, but it actually seems to have made the model worse. As you can see, we have quite a high precision score here, and the precision score just tanked when I tried oversampling the minority class. And that may have something to do with, cancelled flights they're very particular. It's probably a very fine line in the decision boundary between a cancelled flight and a non-cancelled flight, but that's just my intuition. Not sure exactly why it worsened the performance. But if we take a look at how it's performing now, you can see we have a very high precision and a low recall. Oh, one more thing I want to do actually before I do that is in here, in the classification report, I want to also include target names to be this list here, so that we'll get the same label names in the classification report. There we go, not cancelled and cancelled. So if we look, you can see not cancelled knocked it out of the park. Obviously, I mean, we have so much data for this class. Did extremely well. We predicted 99% of them correct. We predicted out of all the ones 99. Okay, so out of all the ones we predicted not cancelled, we got 99% of those correct. So that's what the precision of 0.99 means. And out of all the actual not cancelled, which are these are the actual values, you can see we got it rounds up to 100% correct. So recall 1.0. But now in the minority class, the cancelled class, we have precision of 0.95, which is very good. That means out of all of the predicted cancels, we got 95% of them correct. But our recall is quite low, which means out of all the actual cancelled examples, we only got 51% correct. So it's saying that our model, it rarely mispredicts a cancelled example. When it's cancelled, it's very good at knowing it's cancelled. You can see it only got 9 of those. It only classified 9 not cancelled incorrectly as cancelled. However, it also made a lot of cancelled predictions on the cancelled class, which it shouldn't have. So if you consider this as the positive class and this as the negative class, you can see we have a high number of false positives and a low number of false positives and a high number of false negatives. And yeah, so I mean, again, like I said, when I tried adjusting the class imbalance, our number of false positives went way up. This went into the thousands, I believe. And the overall f-score, which is a measure of both the precision and recall, sort of combined, went down to like 0.2 or something. So that will conclude today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.